Welcome back to section 2.3, part 2. We left off on graphs that enlighten, and we are talking about pie charts. So a pie chart is probably something you've seen before, but each slice is proportional to the frequency count for the category. And we'll talk more about that, but features of pie chart, it shows the distribution of categorical data in a really commonly used format. Now, constructing pie charts can be a little difficult, but we want to turn each value into a percentage, and we talked about this earlier, so make sure to check out, I believe it was section 1.1, by taking the frequency for that category and dividing it by the total. And then I like to lightly draw, and I can't lightly draw on this, but I can erase when I'm done. But I like to look at the slices to kind of make sense of what does 50% look like, 25%, etc. And we'll check it out in this example here. So it wants us to construct a pie chart of the stolen boats. So the first thing I need to do is figure out what values each of these are. So this bar, the jet ski bar here, looks a lot like 1350, and these are not perfect. So we've got, this looks a lot like 900, and let's just say 380 and 350. Those are pretty similar, and then 50. And so I'm going to add up all these numbers. And so that means a total of how many stolen boats. Looks like when I add them all up, I get 3,030. So to figure out the percentages, I'm going to take each value and divide it by the total. So divide each of these by the total. And I end up with jet skis gives me, I believe that says 48%. Sometimes I can't even read my own handwriting. This one is 30%, and 13%, and 12%, and 2%. So when I say lightly cut, what I do, and y'all have seen my drawings at this point, so you know that I don't have a steady hand here, but I just like to kind of see what's going on. And each of these slices is 25%, and then I like to kind of go from there. So 48% is really close to 50%. So don't get mad, but I'm going to just say it's 50-ish. Oh, the other thing is I want to add these up. When I added them up, I got 102%, and that's just okay. If you get 107%, you want to double check your stuff. We were estimating anywhere within like a couple percentage points, you're okay. So I'm going to erase this part here, and I'm just going to call this jet ski, 48%. Now, 30% is a little more than 25, so I'll give it just a little bit more there, and I'm going to call that motorboat, and that's 30%. And now these slices get a little tricky. So about half of this here is 15 and 15, right? Because, I'm sorry, it's 10 and 10, because we've got about 20% left there. So, I mean, this one is about that, and then I want this one to be a little bit smaller, and then that to be a little bit more. So it's not perfect, and hopefully you have a steadier hand. If you use a ruler, you can also use colored pencils, and there you go. All right, you go ahead and give it a try with the Pareto chart that you built in the last example. And that's the solution. The next thing we're going to be talking about is a frequency polygon. A frequency polygon is a graph using line segments that connect points located directly above class midpoint values. So we're using the midpoints from a frequency distribution. It's very similar to a histogram, but instead of bars, we're using points. And again, it's just a different way to display data. You can also use a relative frequency. The only difference, remember, relative frequency is we're talking about percentages. That's it. When you construct a frequency polygon, you need the frequency distribution table. You need the midpoints for each class. Those midpoints become your horizontal axis. And then to determine the scale for your frequencies, see how this only goes up to 25? That would have to do with the frequencies for the data you have. So if you have frequencies that go up to 100, this vertical axis isn't high enough. So let's look at the frequency polygon and the frequency distribution. And we're just going to describe the relationship between the two to see if we can make sense of this. So the first thing I notice is that the midpoints of the class are on the x-axis. So the midpoint of this is 99.5. And look at that. That corresponds to 11. And then this one here is 149.5, and that corresponds to 24. So I can see where these come from. Another thing I notice is that it actually starts with the class before and the class after. The first midpoint here is 99.5, but it wants to start at the 0 and end at the 0. So that's a little bit different. What else do you notice about this graph? And then go ahead and give one a try. So construct this frequency polygon. Remember how to build it. You can go back to the constructing and press play when you're ready to see the solution. And there you go. Now we're going to talk about graphs that deceive. So we're going to focus on two main ways that you can deceive with graphs. And I encourage you to, as you start consuming data in the real world, watching the news, reading different things online, to look for these and consider what they're trying to tell you. So the first is a non-vertical axis. So non-zero, excuse me. A common deceptive graph involves using a vertical axis scale that starts at some value greater than 0 to exaggerate the difference. So if you're trying to exaggerate the difference between two groups, then you're not going to start at 0. So this graph starts at 10% and this one starts at 0%. Let's look at these two graphs. So these come from the same data. From a clinical trial of OxyContin, a drug used to treat moderate to severe pain. The results of that clinical trial included the percentages of subjects who experienced nausea in an OxyContin treatment group and the percentage in a group given a placebo. So just take a moment and look at these graphs. Why would someone want to use the misleading graph? What are they trying to say? So if I was using this misleading graph here, I am clearly trying to say that if you take OxyContin, you are going to get a lot of nausea. And in fact, I'm trying to show that it is like way bigger, like 10 or 20 times bigger. It's actually 12 times bigger that they're showing here. And I'm trying to say like, wow, if you take this, you are like gonna get nauseous. But if you look at this graph over here with a 0 axis, you can see that really it's more like half of the people, like 2 to 1. And so it's not quite as extreme where it feels like this one is saying like 100% guaranteed. And maybe they're trying to say it because they want to discourage recreational use of OxyContin. And okay, that's great. But you just need to consider why people are doing it and what they might be trying to say. Go ahead and give it a try in this self-driving vehicles and press play when you're ready to see an answer. And lastly, pictographs. So pictographs are drawings of objects, and it's data that's one-dimensional in nature, so maybe budget amounts, but it's shown with 2 dimensions, like dollar bills, or 3 dimensions, like coins. And by using the pictographs, they can grossly distort differences by using some principles of geometry. And you can read those there. We'll take a look at this example. Consider the data here. Why would someone want to use this misleading graph, and what is it trying to say? So take a moment and just read it over. So we see in 1970, 37% of adults smoked, and in 2013, 18% of adults smoked. When I just look at this, I think like bigger, like that's all I see. It's not just like the same size. I mean, it's like longer, wider. It's way, way, way bigger. So what I see is like it's like 8 times bigger, 8 times more. But if you actually look at the percentages, I mean, it's closer to double or half, if you will. And so the pictograph is really trying to say that it looks like a lot more people used to smoke than they do now, but really it's just double. Go ahead and give this one a try. And there's the solution. And we'll just kind of end with some concluding thoughts here. You want to make sure for small data small data sets of 20 values or fewer, just use a table instead of a graph. It's not enough information. Focus on the true nature of the data. Don't try to make it too designy and catchy. Just really focus on the data. Don't distort it, and pay attention as you start to consume data around you. And that concludes section 2.3.